Okay, welcome to lecture here. We're continuing on with chapter 14. Right here. Okay, so like I said, we're continuing on with chapter 14, which is sort of acid and bases, acid base equilibrium, a lot of stuff in this chapter. So last time we talked about weak base equilibrium. So weak base equilibrium pretty much works the same way as weak acid equilibrium. Because it's a weak base, it's not going to fully dissociate. It will kind of mainly stay together. And that means that we do get an equilibrium situation that sets up. So that means when we do those problems, we do have to do an ice table again. So again, anything that pretty much involves a reversible reaction, some type of equilibrium is going to involve an ice table calculation. We're going to do the ice table like normal, which means if you can make an assumption, you can make the assumption. Um, if you can't, you need to solve it, through the quadratic formula or something like that. The main difference, though, is sort of the outcome of that ice table. In the sense, we'll still be solving for x, but the end result of that is that when we do solve for x, it actually is going to be the hydroxide concentration. Again, because it's a base, it should be producing OH minus on the product side. So when we do get that X, again, not going to be our H plus concentration, but going to be our OH minus concentration. That again will allow us to go into the POH equation first. And then once we get the POH, we can subtract 14 and get us to the pH. So kind of the same steps really as a weak acid or really any type of equilibrium type problem. Again, the main difference is because it's a weak base, we should be producing that hydroxide. And again, first usually has to go POH first and then to the pH to get us over there where we need. We also talked about, I think at the end as well, acids and sort of ways you can look at acids and try to help determine, sort of the acid strength, which acid may be a stronger acid than another. And we sort of broke up the acids into sort of two types, ones that contain oxygen and ones that do not contain oxygen. And pretty much for the ones that do not contain oxygen, for example, all the ones from really group 7, like HF, HCl, HBr, HI, what we overwhelmingly look at in terms of trying to determine what acid would be stronger is what is known as bond enthalpy or bond strength. So the stronger the bond enthalpy, which is the energy required basically to break the bond between the hydrogen and say the F, or the hydrogen and the Cl, the stronger that bond is, the weaker the acid's going to be. Because remember that what makes something an acid is the ability to basically give away the H plus or produce the H plus. So you got to break that bond in order to do that. And that means that if it's much harder to break that bond, it's going to be a much weaker acid because of that. So the general trend, if you do look at group 7, is bond energy increases as you go up towards fluorine. Fluorine is the strongest in terms of bond energy, and that means that fluorine there with the hydrogen would be the weakest acid out of the bunch there, HF. And acid strength would actually increase as you go down. So HI would be a stronger acid, again, has a weaker bond energy, which means does not take a lot of energy to break that bond. Thus, it could produce H plus a lot easier. And because it can produce H plus a lot easier, it is considered a stronger acid. Now, when we do have acids that have oxygen in it, there's really kind of two situations that sort of occur with those guys. One situation is kind of we have the different central atom, but everything is on the outside is pretty much the same. Are weaker acids more reactive because of a weaker bond? No, it's just a stronger acid, so it'll be able to produce it will be able to produce H plus easier, the stronger acid. So in comparison, say, of HI to HF, HI is a stronger acid because it actually has a weaker bond. And because it has a weaker bond, it is a stronger acid. It's able to really release that H plus more. So in that sense, HI would be perhaps more reactive than HF in that sense of an acid perspective. But weaker acids are not more reactive usually in that sense. Again, in the sense of producing H plus, weaker acids would actually produce probably less H plus or free H plus in that case because of that stronger bond. Now, in the case of the oxygens, if we have sort of a different central atom, but everything on the outside is the same, the overwhelmingly thing that we look at in those acids, which are referred to as oxyacids, is we actually look at electronegativity. And the greater the electronegativity, the greater the acid is going to be. Again, the higher the electronegativity of that central atom is going to bring those electrons in, and that's going to weaken that OH bond. And weakening that OH bond is going to make it a stronger acid. So in that case, the electronegativity of the central atom is important. Higher electronegativity, stronger acid. The other sort of oxyacid situation is where we have the same central atom, but different outside atoms. So because it's the same central atom, it obviously will have the same electronegativity. So you cannot look at electronegativity there. So what we look at is oxidation number. And the one with the higher oxidation number will be the stronger acid. Again, same idea, higher the positive oxidation number on that central atom, going to bring those electrons in closer, going to weaken that OH bond and allow that H to come off easier, and thus making it a stronger acid in that case. All right, so I think that's about where we sort of left off. Any questions on that there? Okay, so where we're at is salts. So let's talk a little bit about salts, and just a reminder that we do get salts from basically a reaction of a acid plus a base, right? Will typically give us a salt and water. So a salt is really just an ionic compound, basically a positive guy, negative guy. Now, the formation of this salt itself, which usually comes from the reaction of an acid and a base, the salt itself can then perhaps go on and continue to react. And in certain cases, it can continue to react, and it will react basically with, you know, what's there, which means it's going to react perhaps with water at some point. So if it does continue to react with water, what's essentially going to happen is it's going to have an effect on the pH of the solution. It may make it acidic, it may make it basic, depending on sort of the reaction that occurs. So there are certain salts, though, that are considered neutral salts. And neutral salts are really salts that contain an alkali metal or an alkaline earth metal, except for beryllium, and the conjugate base of a strong acid. So I'll add that in there. And the conjugate base of a strong acid. Like something like Cl minus, Br minus, NO3 minus. So if you remember, there's sort of an important relationship that we talked about earlier on in this chapter, and this is really where we see that relationship or the importance of that relationship, and that is if something comes from a strong acid or a strong base, its conjugate partner is going to be relatively weak. And what that means is it will not go through any type of hydrolysis reactions. It won't react with water. Now, if something comes from a weak acid or a weak base, its partner is going to be relatively strong, its conjugate partner. And that will continue on and react in this case. So if we do have something from a salt that comes from really group 1 or group 2 on the periodic table, if you remember, group 1 and group 2 on the periodic table is really where a lot of our strong bases come from. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, all those guys. So group 1 and group 2, again, is really basic area on the periodic table. It is where a lot of strong bases come from. So if you have a salt that contains any of those guys from there, it's going to be a neutral salt. So we would expect it to have a neutral pH, which means we would expect the pH here to be 7 in this case. So when we look at something like sodium chloride here, this salt, we could kind of think about, you know, if you kind of think about the step backwards, like that's the salt. So if we think about backwards, where perhaps that salt might have come from, there's probably a good chance that this salt most likely came from the reaction of sodium hydroxide and hydrochloric acid. Hydrochloric acid is a strong acid. The Cl minus part here would be its conjugate base, and it will be relatively weak because it came from a strong acid. So this will not do anything in terms of, you know, really working with water. The Na plus most likely came from sodium hydroxide, also a strong base, and it's also part of group 1, and it also will not go on and further react. So anything that is typically from a strong acid or strong base, the salt, that it kind of originated from there. And again, sometimes it's helpful to think about these things sort of one step backwards. You know, this is sort of where it came from. It will not go through any type of hydrolysis, which is the reaction with water, and it basically will be a neutral salt. And there's really no calculation involved here. All you have to do really is sort of put a pH of 7, and that essentially is what the answer should be. Now, there are salts that are sometimes referred to as basic salts. So for example here, these are salts that are derived from a strong base and a weak acid. So derived from a strong base and a weak acid. So for example, if we take the salt sodium acetate, this sodium acetate really breaks apart into two things. It breaks apart into a sodium ion and an acetate ion. And again, if we sort of think about where this guy came from in terms of his reaction, it most likely came from a reaction of a strong base like sodium hydroxide and a weak acid like acetic acid. So this salt that we're looking at right now probably came from that reaction right there. So when we go to analyze sort of the parts of the salt here, the sodium most likely came from sodium hydroxide, which is a strong base, which means this guy is going to be relatively weak and really neutral, as we see up here. It is also part of group 1. But when we look at the acetate part, the acetate part came from probably acetic acid. Acetic acid is a weak acid, which means its conjugate base over here is going to be relatively strong. And what that means is the acetate part of this, not the sodium part, but really just the acetate part will continue to react once it's produced in solution. And as I mentioned earlier, what this salt reacts with is pretty much the other thing that's present, which is water. And this is why it's sometimes referred to as a hydrolysis reaction, because it is a reaction with water. Now, the question is, what happens when acetate reacts with water? And the answer is, it's going to do what it normally would do. And what I mean by that is, we know that it came from acetic acid, which means that the acetate would be the conjugate base. And that means when the acetate reacts with water, it's going to react as a base, which means it's going to accept the H+. So it will accept the H+ because it's going to act here as a base because it came from an acid. And when it does that, it will make acetic acid, which, by the way, it always makes where it came from. And it will make some hydroxide here. So this is the hydrolysis reaction that's taking place. The acetate that is produced from the sodium acetate, or that salt, will react with water because it's relatively strong. It will react as a base and accept the H+. And this reaction right here, if you write it correctly, gives you a lot of information without actually doing any type of calculation. We will know that this solution will be basic. We know it will be basic because we produced hydroxide. So again, we produce free hydroxide on the product side. So we know that this guy will be a basic solution without actually doing a calculation. If we did the calculation, this is a sort of weak base sort of reaction here. It's a reversible reaction, and it requires an ice table. And you would do an ice table here. If you needed to solve this, you would do an ice table. You would solve for X, and X would equal the hydroxide concentration. That would then get you the POH and then to the pH. Now, if you remember, I also mentioned when we talked about Kw equals Ka times Kb. So if you remember, I think the other day we also talked about this relationship, that the Kw equals the Ka times the Kb. These problems here are the problems here with salts is the place where you will oftentimes need to use that relationship, because in this particular problem, they probably would give you the Ka value for acetic acid. But in this particular problem, you don't need a Ka value because you should be using a Kb value. And again, that's because we produce hydroxide. So as we talked about before, if you produce hydroxide on the product side and you're doing a calculation, you really should be using a Kb. If you produce H plus or H3O plus on the product side, probably a Ka value you should be using if it's that type of problem. So salt problems, hydrolysis problems, they historically give you the wrong K value. So I'll just put it that way. They give you the wrong K value. They oftentimes will give you the Ka value when you should be using the Kb value when you should be using the Ka value. So again, definitely here that Kw relationship is one that's used a lot. Any questions on basic salts? So obviously there's neutral salts. We have basic salts. Basic salts, again, essentially comes from a weak acid. So we must have salts that are acidic, and we do. We have salts that are acidic, and those acidic salts are derived from a strong acid and a weak base. So for example, if we had the salt ammonium chloride, and if we have this salt ammonium chloride, when it breaks apart, it is going to break apart into ammonium ions and chloride ions. So when we think about this salt here, again, if we sort of take a step back and think about where it came from, if you were asked where did this salt come from, probably a good answer would be HCl, hydrochloric acid, and the weak base here would be ammonia. And again, this is going to allow you to understand certain things. For example, the chloride here, like we saw at the very beginning, comes from HCl, which is a strong acid, which means the chloride should be relatively weak or neutral. So this guy is going to be neutral here, as we talked about at the beginning. And basically what that means is it will not react with water. It will not affect the pH of the solution. So that leaves us just the NH4 plus. And as from what we guessed here, it most likely came from ammonia. Ammonia is a weak base. And understanding that that is a weak base, that means that technically our ammonium here, NH4 plus, is the conjugate acid. And it'll be relatively strong because it comes from a weak base. And what that means is we would expect in this case the NH4 plus to continue to react. And what it's going to continue to react with, again, is water in these hydrolysis reactions. And the idea of understanding that the NH4 plus is really an acid means that when it reacts with water, it's going to do what an acid does, and that means it's going to actually donate the H plus over. When it donates the H plus over, much like we saw in the last one, it will always produce where it came from. So it will produce some NH3. When it does so, we will also produce some H3O plus as well. Any questions on that reaction? So just like last time, without doing any type of calculation, we should know that this solution is going to be acidic because we are producing H3O plus, which means we should know, and why that's really important to understand, for example, in this one, that we would expect the solution to be acidic, or in the previous one, we would expect the solution to be basic. The importance of understanding that is when you go do your calculation, you will know if your number actually makes sense. So before you even pick up the calculator, you know you should get an acidic pH. You should get something below 7. And just like in the previous example, you know that guy was going to be basic. So before you even pick up your calculator to do your calculations, you should know it should be above 7. So these are things you definitely want to think about as you go through the calculations, just to make sure, A, you didn't mess up the calculation, and B, that, you know, your number does sort of make sense when you do the calculation. So that's why it's really critical to understand and be able to write these reactions, be able to look at them and understand what's going on in them so that you could correctly identify these things. What that means is in this situation, it is still kind of a weak equilibrium type situation. If you want to do a calculation, going to require an ice table. Here you would solve for X, and X actually would equal the H plus concentration, which means you could go right into the pH at that point. So again, it's going to require an ice table. You're going to solve for X, and it will give you a acidic pH. Same deal here. You most likely will be given the Kb value, but because this is acidic, you actually need the Ka value. So again, here you're going to have to probably use Kw to get the right value, and make sure that you are using the correct K value. So as we talked about a number of times up to this point, the easiest way to sort of determine should you be using Ka or Kb is looking at your actual equation, which is why it's important to write them correctly and see what you have on the product side. So again, if you have H3O plus, should be using a Ka. If you got a OH minus, should be using a Kb value. So this is one way that we could generate an acidic solution or an acidic salt. There's actually another way that is possible, and that is with the small, highly charged cations. So highly charged positive cations can basically produce an acidic solution. So for example, if we had aluminum basically surrounded by water, and when this is in water, what's going to happen is we will produce something like this. So we will produce something that looks like this here. And what's happening here is, let me just kind of draw a picture. Basically, what we have is this aluminum that has a +3 charge, a kind of small, highly positive type charge. And what this means is there's basically 6 waters that's attached to it. So we have basically 6 waters. And I'll just draw out one of the waters here. Again, it would be attached by the oxygen, which is more negative, just so we know. So we basically have the 6 waters that are surrounding this this aluminum ion, and that's basically what it means when we write aqueous next to something. We don't usually include the water part of it because it gets a little messy in the equations, but that's basically what it means when we put the aqueous next to it. So what happens in this situation is we have this ion that's in solution, this cation, it's surrounded by these waters, and what ends up happening is another water, not attached to an aluminum, comes over and basically will grab off one of those H's from the water that's attached to the aluminum. And that is how we end up producing that H3O plus. Again, if you add an H plus to water, you get H3O plus. And this giant thing that's kind of left over here, you may be wondering kind of like what's going on with this, is if you just keep track of everything, there is an aluminum. There's one aluminum. There is 1, 2, 3, 4, and 5 waters that are still intact, which is why we have the 5 waters is still intact. When this guy loses that H, he is left as OH, which is where this comes from. And that's OH minus, so -1 and +3 leaves us a +2 that's left over. So that's where all the parts come from. But ultimately, what the importance is in terms of what we're talking about in this case is we have now just produced H3O plus. And H3O plus should tell us that this solution should be acidic. And we would expect an acidic solution in this case. So small, highly charged metals, a lot of times aluminum, maybe chromium, beryllium, some transition metals, copper, things like that, in these sort of complex ions like it is here on the left, can react with water and produce H3O plus and thus be considered sort of an acidic salt in that particular case. Any questions on those sort of 3 things here? Okay, let us take a look at some examples here. It's everything we just talked about. All right, so why don't you start with this one here, take a minute or so and think about it. What is the pH of a 0.45 molar KCl solution? So think about what you think it might be. We'll talk about what it is in just a second. Okay, so let's take a look. So again, if you're analyzing this and trying to figure out what's going on, the actual formula is a pretty good place to start with. So when we look at KCl, that is the salt, is an ionic compound. It will break apart really into K plus and Cl minus. So really what you're looking for are looking at in these type of problems is you want to look at both parts of the salt, and you want to determine if any part of the salt will continue to react with water and go through hydrolysis. In certain cases, it may not. In certain cases, one may. In certain cases, as we'll talk about, maybe both will react. So if it helps you decide sort of what's going on, you may want to think about it, like I said, like a step backwards. So if we produce this salt, if I had to venture a guess here, this salt most likely came from a reaction of KOH and like HCl. The K plus most likely coming from the KOH, the Cl minus most likely coming from the HCl. And what we want to determine is, are these guys relatively weak or relatively strong? So again, it's that opposite relationship. KOH, which is a strong base, means that the K plus here, which is also group 1, is going to be relatively weak. And that means that it is actually a neutral salt. So we wouldn't expect the K plus to do anything because it's from group 1. Cl minus came from HCl, which is a strong acid, which means again here, this guy should be relatively weak. And as we saw, would also be considered a neutral salt, which means this guy altogether, both parts of it is neutral and no calculation needed here. We would expect the pH here to be 7 in this case, which would be neutral. Question on sort of the reasoning behind how we got there. Okay. So why don't we look at one where there really is some calculations to be done. So why don't you give this a go, see what you come up with. So you actually do need to do a calculation here. And I'll let you give it a go and give it a try. Then we'll talk about it. So here what we're trying to do is figure out the pH of this salt solution of sodium fluoride. Has a concentration of 0.3 molar, and the Ka for HF is 7.2 times 10 to the minus 4. So why don't you take a few minutes and give it a go, and then we'll do it here together and see how you were doing. So again, think about everything we talked about. Think about, what type of salt it is, what should be happening. See if you can get, obviously, the equation written for what's going on. Start the ice table like normal, kind of see how you go. And again, we will talk about it in just a few minutes. But why don't you give it a try and see what you come up with. Okay, so let's kind of see how we're doing, how you're progressing. So again, you want to approach this the same way. Hopefully you could recognize that the sodium fluoride here is a salt. So again, you really want to think about what's going to happen when it breaks apart in the solution. And when it is in solution, it's not going to stay together. It will break apart into sodium ions and fluoride ions. And again, you might want to think about where this guy came from. So if I had to venture a guess, I would say it probably came from sodium hydroxide and hydrofluoric acid. You may say, how do I know it was hydrofluoric acid? Let me also point out that there's a lot of really important information usually given to you in the problem. That right there is a pretty big hint of where it came from. Yeah, so right there, the Ka value that they gave us. Also, if you weren't sure, Ka again means it's a weak acid. So we know that this is a weak acid and we know this is a strong base. Also, what that means is the sodium, again, most likely came from the strong base, which means it is also group 1 as well. It is a neutral salt and really will not affect the pH. The F minus came from HF, which is a weak acid. And because it's a weak acid, we know it's going to be a relatively strong conjugate base. And this guy, because it does come from a weak acid, will continue on and react with water in a hydrolysis reaction. So that is really the reaction that we want to get down correct. That is going to be F minus. And again, if you're not sure what's going to happen when it reacts with water, this will help you understand it. Since you identified it as a conjugate base, it should do what a base does, and that means that it should accept the H plus when it reacts with the water. By the way, logic also tells you it doesn't have an H, so it can't give it, so it's got to accept it in this case. So don't overlook logical explanations as well. And what that means is we should get HF and OH minus. Now, a couple of things about this reaction that we just wrote and what we got. First off, you always produce where it came from, which is also a very big hint. Again, people really struggle with getting the reaction down and the equation down. You want to look for all those helpful things in the problem that will help you sort of determine that. The second, and maybe more important in terms of the aspect of what we're solving for here, is we have produced OH minus, which means even before I pick up the calculator, I know that this thing should be basic. So I should end up with a basic pH just from the reaction. Don't even have to do the calculation. I should know it actually is basic. Any questions up to that point there? All right. So
Sorry. So again, why does the like sodium hydroxide not like matter in this equation?
the sodium hydroxide doesn't matter because it's a strong base. So basically, the relationship is anything that comes from either a strong acid or a strong base, its partner will be relatively weak, which means it will not react with anything. It's kind of neutral. And anything that comes from a weak acid or weak base is relatively strong, its partner, and it will continue on to react with water. So because the Na plus part of the salt came from really sodium hydroxide, um, it's not going to continue to react because it's basically weak and neutral.
Okay.
And the sodium hydroxide really is not any part of the reaction here, really, because it's not what's reacting. It is these guys up here, this guy, and this guy. These are like the step before when these guys react. That's when we produce NaF and some H2O. What we're looking at here in this problem is now this reaction between these two guys. So this is now where we're at. So we're these guys up here are sort of the step before this problem. And now that we're at this problem, we're actually looking at the reaction between these two guys right here.
Okay. And how do we know that sodium hydroxide is like a strong base?
It's just some of those ones that you should know. It's a strong base. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. So we talked about it the other day in lecture. Pretty much most things that have OH in the formula, and that are group 1 and group 2 that have OH in it, for the most part, most of those guys are going to be your strong bases. Other questions? Okay, so now that we have sort of the reaction that's actually taking place, we want to do an ice table here. So we're going to do our ice table, kind of like a normal ice table. And in this case, we have 0.3 molar sodium fluoride. So when sodium fluoride breaks apart, it does break apart into a 1-to-1 relationship, which means our concentration of fluoride would be 0.3. This guy is going to be 0 and 0. The change here would be minus x, plus x, and plus x. And at equilibrium, 0.3 minus x, x, and x in this particular case. Here again, like we talked about before, I'm not really putting anything down there for the water. Water is a liquid, right? So it's not going to participate in the equilibrium. So again, it's always a good idea not to put numbers or X's in things that you're not going to eventually use, so you don't try to use it incorrectly. This is going to go into our equilibrium expression. So our K in this case is going to be our products, which is HF and OH minus, divided by F minus. Now, the other important thing that we get from this equation or this reaction is it's going to be basic. And because I produced hydroxide here, I need a KB. So as you can see, as I talked about before, this is these problems where they historically give you the wrong K value. So you definitely should be using a KB value in this case, not a Ka value like they gave us. So again, very common that they do give you sort of the wrong K value. And it's very common people don't think in these problems and they just roll with the value that was given to them. And if you do, you will get it wrong because we're doing a base type problem here, not an acid type problem. So I should hopefully have, I hope. Oops. All right, so let's see where I could go with that next. What we want to do is we want to solve for KB. So we're going to use KW equals KA times KB. So the KB here would be 1 times 10 to the minus 14 divided by our Ka value that was given to us, 7.2 times 10 to the minus 4. And if we do that, we get like a 1.4 times 10 to the minus 11 as our KB value. So we definitely want to use that KB value. So what I'm going to do is actually I'm going to go back a page here. So I got somewhere to write on. So I ran out of room there. Let's just clear all that stuff. All right. So continue on with our problem that we just did. We now have our KB is equal to our HF times our OH minus divided by our F minus. And solving for our KB, that was 1.4 times 10 to the minus 11. At this point, we're going to substitute in our equilibrium lines. So what we had was, if we go back there, we had x squared over 0.3 minus x. So that will give us x squared over 0.3 minus x equals 1.4 times 10 to the minus 11. Since this is a small value of k, we could assume that x is equal to 0. And if we do that, that gets us x squared over 0.3 equals 1.4 times 10 to the minus 11. We're going to multiply the 0.3 to the other side and also take the square root of it. So take 0.3 times that and also do a little square root action. That is not the square root button. Try the right button there. There we go. No, still wrong. Square root. There you go. We should end up with something like an x value of 2.04 times 10 to the minus 6. Remember that we do want to check it. So we're going to take this and divide it by 0.3, times it by 100 to check it, and divide it by 0.3, times it by 100. And the check's good. It's not even 1%. It's way less. So the check is good. So that means that this guy would then equal from our ice table, again, not our H plus concentration, but it equals here our OH minus concentration. So that gives us our OH minus concentration. So we then can find the POH by taking minus the log of that number there. And if we do that, and calculator doesn't die, come here. 2.04 to the minus 6. So if we do the POH equals minus the log of the OH minus, which in this case would be minus the log of 2.04 times 10 to the minus 6 equals 5.69. Now, at this point, if for some reason you were confused and you thought this was the pH answer, by understanding the equation that you wrote, that should not make sense to you, because if you thought this for some reason was the pH and you got a 5.69, that is an acidic pH, so it definitely is wrong somewhere. So again, these are things you want to think about as you're doing these calculations. I've seen it happen a lot of times. You know, people just kind of roll with it without thinking, and they either use the Ka value, they get a pH value they think that's acidic, when obviously should be basic. So we do need to do that last step here. Taking the pH would equal 14 minus the POH. That gives us 14 minus 5.69. And that's going to get us a pH, we'll call it 8.31. And this pH here does make sense. It is basic. And that's exactly what we would expect to have happened in this particular problem, based on our reaction that's written. So although I'm keep harping on making sure that you write these reactions correctly, it is extremely important for your success in these problems, because if you start out with the wrong equation, and I've seen it done, I've seen people write that equation and produce somehow H plus or H3O plus, you're going to end up with an acidic pH and you're going to get the wrong answer in this particular case. So everything really does start with being able to correctly sort of write these equations so that you can get the calculation part correct, and again, keeps you sort of thinking the correct way. Any questions along the way here on this particular one? Okay, so again, let's try one here. I'll give you another one here to do. See what you come up with. What have we got next there? All right, so why don't you give this one a go. What is the pH of a 0.75 molar sodium cyanide solution? The Ka for cyanic acid there is, hydrocyanic acid is 6.2 times 10 to the minus 10. All right, so see what you come up with. Take a few minutes here and calculate it up. Okay, so let us take a look and kind of see how we're doing. So again, we have sodium cyanide here. So we want to think about sodium cyanide when it's in solution. Again, it is not going to stay together. It is going to pretty much 100% break apart into two ions. It's going to be a sodium ion and cyanide here. So when we're doing these type problems involve salt, what we're really looking at is both of these guys, and we want to know, is any of these guys going to be strong enough to react with water in a hydrolysis reaction? So at this point, we've talked about sodium a lot. It most likely came from sodium hydroxide. It is group 1. It is a neutral salt, so it is not going to affect the pH of the solution. That pretty much just leaves us Cn minus. Cn minus, if you're not sure of, again, you could look at the problem, gives you a big hint. Cn minus probably came from HCN. HCN has a Ka value, which tells us that HCN is a weak acid, which means our Cn minus here would be a relatively strong conjugate base, as sort of the relationship there. And what that also tells you is it then should react with water. So it's going to react with water, and understanding that relationship tells you what it should do when it reacts with water. And because it's a conjugate base, it will do what a base does and accept an H plus. When it accepts that H plus, it will produce where it came from, which is HCN, which always is the case. So again, another big hint as to what should go on the product side there. And more importantly, when it does that, it is going to produce hydroxide. And again, also a super big hint. I now know that before I even touch my calculator, I should end up with a basic answer. Any questions on sort of getting to that equation or writing that reaction? All right, so now we should ice table it up. If I get things out of my way, maybe. That's a really bad eye. So initially here we do have 0.75 molar, 0 and 0. Change going to be minus x, and plus x, which means when we get to equilibrium, 0.75 minus x, and x. This is going to go into our K expression here. It's going to be our products over reactants. And this should be a KB. Again, we see as basic, we see hydroxide. I should be doing a KB at this point, much like very, very super common in these problems, not given a KB, but given a Ka. So we do need to use that Kw relationship. So in this case, the Kb will equal our Kw divided by Ka. Kw being 1 times 10 to the minus 14 divided by our 6.2 times 10 to the minus 10. And that will get you looks like 1.6 to the minus 5 would be our Kb value here. So putting in our equilibrium line, we have x squared over 0.75 minus x equals, again here, our Kb value, not the Ka value. We're going to assume that x is equal to 0 here. And basically, we're going to take our Kb value times it by 0.75. Going to take a little square root of it. And that does give us an x value of, looks like 3.48 times 10 to the minus 3. Again, multiplying 0.75 times 1.6 times 10 to the minus 5, and then taking the square root of it. We do need to check it, so we're going to take that number, divide it by 0.75, and times it by 100, and I believe we're nowhere even near 1%. So again, our assumptions should be good here. In a lot of cases, on these sort of guys. Usually your assumption's good. You should definitely check it though. But I would say a lot of cases, you're usually pretty good. I think it's like 0.4% in this particular case. So the check is good here. And again, we're checking it by dividing by 0.75 and times it by 100. At that point, that means that our X value here, which is 3.48 times 10 to the minus 3 molar, equals our hydroxide concentration. So again, that is going to allow you to calculate the POH and not the pH directly here. And that means that our POH will equal minus the log of 3.48 times 10 to the minus 3. And that gets you a POH of 246. Remember, again, not the pH. So to get the pH, 14 minus 2.46. Looks like 1154 on the pH of the solution. And that is definitely basic, which is what we would expect it to be. So again, if for some reason you thought this number here was the pH, knowing that it should be basic, that should hopefully help you correct any mistake you're about to make. And again, here 11.54 would definitely be basic. Question on any of those steps, where any numbers came from, why we did anything? Okay. So again, salts in these couple examples here were basic. You could have, again, an acidic salt, works the exact same way. You're going to do an ice table. The only difference if you have an acidic salt is when you hit X, like we talked about, that actually will be the H plus concentration, and you could just slap it into the pH equation at that point. So pretty much identical to these. So just kind of finishing up here, talking about salts. Here's a much prettier picture of what I drew in terms of the aluminum, but basically what this is representing here is that's aluminum in the middle. Each of these are waters on the outside. And again, this is another way we could get that acidic salt. Just another water comes over and basically plucks off an H. And again, producing that H3O plus, going to be a acidic solution. So small metal ions, complex ions surrounded by water and some other things, again, have that ability to sort of be acidic as well because of this sort of reaction that's taking place. Maybe a better picture than mine. Now, up until this point, we've talked about salts where only really one part of the salt could go through hydrolysis. But it is potentially possible that you could have a salt where both parts, for example, went through hydrolysis. So, for example, if you had something like ammonium fluoride. Yeah. So if you had something like ammonium fluoride, this guy, when he breaks apart, would be NH4 plus and F minus. So when you look at this NH4 plus, if we again think about it backwards, most likely came from NH3, which is a weak base, which means this guy would go through hydrolysis. And when it went through hydrolysis, it would act as an acid and donate its H plus, and we would expect it to be acidic and H3O plus being produced. Now, when we look at fluoride, as we've seen, most likely came from HF, which is a weak acid, which means the fluoride would also go through hydrolysis, and it would act as a base when it goes through hydrolysis. And when this guy goes through hydrolysis, it would act as a base. It would accept the H plus from water, and it would produce hydroxide and be basic. So there is potential that both parts of the salt, not just one part like we've seen, can go through hydrolysis. So the calculations are pretty complicated in that sort of situation. So usually what we do in that situation is if we are confronted with a salt where both parts, the positive guy, the cation, and the anion, the negative guy, can go through hydrolysis, we actually do a comparison. And what we compare is the Ka value to the Kb value. And whichever one is sort of larger, that is sort of what we assume the solution would be. So in a situation where both salts can go through hydrolysis, as I mentioned before, whoops, come back. There you go. What we would do is we would do a comparison of the Ka value to the Kb value. We would look at the Ka value for the cation and the Kb value for the anion, and we would determine which one is larger. So if the Kb value is larger than the Ka, easy way to remember that, Kb basic, Ka acidic, the basic is bigger than the acidic, we would assume that the solution would be basic. And what that means is we would typically do the calculation as a Kb calculation and just do it for the anion. So we would just do the calculation, assuming that's going to be a basic solution using the Kb value. We would ignore the cation in this case. So we would just do it for the Kb. If you do it and the Kb value is less than the Ka value, so the acid part sort of larger than the base part, we would assume that this solution would be acidic. And the same idea here, if you were going to do that calculation, you pretty much would ignore the anion or the base part, and you would just do the calculation as an acid calculation, and you should end up with an acidic pH in that case. Now, if the Kb is fairly close to the Ka value, we would assume that the solution would be neutral. So if you do come across a salt where, again, you've identified that both parts of the salt have the potential to react with water and go through hydrolysis, what we do is we then look at the Ka and the Kb values, and whichever one is larger, that is essentially the calculation that you should do. So again, if the Kb is larger, you should be doing a hydrolysis reaction that produces hydroxide. So you should have an anion plus some water. It's going to accept the H plus, and you should produce hydroxide and use your Kb. The Ka is larger, then you would do it for the cation, and it will kind of donate its H plus this way, and you'll make H3O plus, and you should be using the Ka value. So again, you may come across salts that can do that. Both parts go through hydrolysis. You want to make sure you look up the Ka and the Kb values, and again, just choose whichever one's larger. That is sort of the approach you should take. Question on salts, how to calculate pH, or any of that type of stuff. Okay. Then let's talk a little bit about oxides. Oxides are substances that contain oxygen, and there are certain oxides, when they react with water, will produce either sort of acids or bases, if you will. So a lot of our hydroxides in group 1 and 2, as we see over here, which again, as we talked about a number of times, alkali metals, alkaline earth metals, all those words basically mean basic. So this is where we find a lot of our basic oxides. So something like sodium oxide, potassium oxide, when they react with water, they essentially will produce like sodium hydroxide, potassium hydroxide, calcium hydroxide. They produce a lot of bases. So our group 1 and group 2 metals with oxygen plus some water will produce a lot of bases. There's a couple hanging out over here that also will do that. But a majority of them, again, can be found in our group 1 and group 2. And as was the earlier question about, is it a strong base? This is where we find a lot of our strong bases, you know, kind of coming down this way on the periodic table. And again, they have hydroxide in them. Now, when we take nonmetals that have oxygen or nonmetal oxides there, when they react with water, they typically will make acids. So that's all of our kind of nonmetal area on the periodic table. All these guys here, when they react with water, will make acids. So for example, if you take CO2 plus some water, we get H2CO3, which is carbonic acid. For example, if we take N2O5 and react it with water, we actually get some nitric acid that is formed. So a lot of our nonmetals that have oxygen in it, when it reacts with water, is how we sort of produce acids. Again, group 1 and group 2, sort of our metals with oxygen, when they react with water, is how we produce a lot of our bases. And then we do have some that are this sort of orangey color here. These are amphoteric oxides. Amphoteric, again, means if something is amphoteric, it means it has the ability to act either as an acid or a base. So you could get either one, kind of for them, from those guys. Could either go both ways, either act as an acid in certain situations or act as a base in certain situations. Any questions on that? Now, we've talked about some definitions of acids and bases, and we want to talk about another definition of acid and bases. We talked about the Uranus acid and bases, which is basically something that can produce H plus or OH minus in solution. Our Bronsted-Lowry definition of an acid and base, a Bronsted acid is something that donates an H plus, and something that accepts an H plus is a Bronsted-Lowry base. So our good friend Lewis, and when we think about Lewis, we think about perhaps Lewis structures. And when we think about Lewis structures, we think about our good friends, the electrons. Yes. So Lewis came up with sort of a definition of acid and bases that surprisingly enough involves electrons. So when we talk about a Lewis acid is something that can accept a pair of electrons. So a Lewis acid is something that will be able to accept a pair of electrons, while a Lewis base is something that can donate a pair of electrons. So in terms of Lewis acid and Lewis base, it is opposite of Bronsted-Lowry definition in terms of accepting and donating. Also different. One is talking about a proton, an H plus, in terms of Bronsted-Lowry. When we talk about Lewis, we're talking about a pair of electrons being donated. Lewis acids and Lewis bases are really kind of important things, especially Lewis bases. We'll see it again in more detail when we talk about in a later chapter, coordination chemistry or transition complex ions and stuff like that. We will see Lewis bases come back around. So Lewis acid, something that accepts an electron, pair of electrons, and Lewis base, something that donates it. So when we think about what might be good Lewis acids or Lewis bases, something that has a positive charge or something that's deficient in electrons makes a really good Lewis acid. It's able to accept those because it's missing electrons. Something that's able to donate electrons is typically something with perhaps a negative charge. If you're a negative charge, that means you were able to gain electrons. And something that is sort of polar and has some non-bonding electrons is also another guy that is really good at sort of donating electrons. So for example, here, if we look at this here, H plus, the plus means it's electron deficient, which makes it a good Lewis acid. And OH minus is sort of a polar guy with these non-bonding electrons. Again, having the ability to donate those electrons over, making the OH minus a base. Same thing here. We have our H plus, which again, deficient in electrons, going to make it a good acid. NH3 is a polar molecule, if you remember for Chem 50, unsymmetrical geometry, polar molecule, meaning that these electrons here are on a more negative part of the molecule and able to be donated over and making the NH3 a base. So if you look at these two examples and we look at it in terms of Lewis acid and bases, we could definitely identify them as Lewis acids and bases. But we also come to the same conclusion of acid and base when we think about a proton being donated. So we look at Bronsted-Lowry definition. The H plus is going to go over this way, making it the acid. The OH minus is going to accept the H plus, which makes it a base. Same thing here. H plus going to go over to the NH3, making the H plus the acid, NH3 the base. So we come to the same conclusion whether you're sort of looking at a Lewis acid and base or you're looking at a Bronsted-Lowry acid and base. The sort of benefit, though, of doing something like a Lewis acid or base or looking at something of a Lewis acid and base is we could actually apply acid and base sort of definitions to things that do not involve an H plus. So an example of that is what we see here. If we look at boron trifluoride, boron is, again from Chem 50, an incomplete octet, which means it actually has less than 8 electrons around it. It is electron deficient, which means it is more than willing to accept that pair of electrons over from the NH3, which would act as the base in that case. And the benefit of this is we actually do not have an H plus being transferred, but we could still look at these two things and identify something as the acid, which would be boron trifluoride, and something as the base, which would be NH3 or ammonia. And again, the nice thing about the Lewis acid definition is it allows you to basically look at things in sort of the acid and base sort of framework without actually having to see a proton or an H plus being accepted or donated. So usually, again, in order for those electrons to be donated, usually has to be part of some type of polar bond, polar molecule. Just because there is perhaps some lone pairs doesn't mean necessarily something can sort of accept it. So again, polar things with non-bonding electrons are really good Lewis bases. Water is also a good Lewis base. NH3 is a very good Lewis base. And again, things with negative charges like Cl minus, Br minus, any of those halogens are good Lewis bases. And like I said before, anything sort of electron deficient is a really good Lewis acid because it's able to accept those electrons that are coming in. Question on Lewis acid and bases. And again, we will see definitely Lewis acids and more so Lewis bases come about in several other parts along the way here when we get to some other chapters. So Lewis bases do sort of pop their head back out again, especially when we start talking about sort of complex ions. Any questions on any of that stuff there? Okay. So I think that's probably a good place to stop since we'll need a lot more time for the next sort of topic there than what we got left. So we will stop here for today in terms of lecture. Today for lab is the last day to, again, we'll use to officially work on the equilibrium experiment. So again, you should be hopefully working on that and working through that. So if you have questions or anything like that, obviously you could ask them during lab. In terms of your exams and stuff like that, I would anticipate probably within the next day, they probably will be back posted up online. So you can take a look and see how you did on that as well. So I'm pretty much done with them. I just got a couple more things to kind of look at. So either maybe later tonight, or if I have time, or sometime tomorrow, I would anticipate that they would be up there for you to take a look at to see how you did and all that kind of stuff. All right, other than that, if you didn't right here, make sure you do so. We'll see everybody at 11:30. Again, final day to work on in class. Not work on permanently, but in class of the equilibrium experiment. All right, I'll see everybody in about 20 minutes or so.